So today we're going once again back to the basics, and we're talking about SIL. What does a SIL mean? How does a product achieve a SIL rating? And then how do end users use that information from that SIL rating? So we're going to dive into all of that today, and we're going to especially look at what the standards say, what IEC 61508 and 511 think about SIL rating and how you can achieve them. And we're going to discuss the different requirements the standard makes for achieving that SIL. We're going to break each of those apart. There's three main requirements we'll look at, and we'll break each of those apart. Then we'll switch gears and talk about how SIL is used by those end users. And if you have a lower than wished SIL, how can you possibly improve that SIL rating? If you are unfamiliar with me or exida, welcome. My name is Loren Stewart. I do a lot of these webinars and blogs, especially things getting back to the basics. I also help a lot of our mechanical customers achieve certification. If you're not familiar with who exida is, we are all over functional safety. So we are involved in the complete supply chain. So if you are an OEM making devices that you want to show their safety and quality in them, we can help you certify those products. We can help you with tools. We can help you with your quality management, the whole way through to the end users using those SIL rated products. We can help you with our software calculations, SIL verifications, help you figure out how much SIL you need in a system and how to achieve all of that. We are a global company. We're all over the world, and actually this map isn't even the most up to date. We've been adding and adding and adding partners and new offices all over. So I like to say no matter where you are, where your customers are, where your products are going, where your products come from, we have someone close by in functional safety, alarm management, or cybersecurity to help you out, to train you, to coach you, to help you with your calculations. Anything you need, we have somebody there to help. And then last thing about exida, and then we'll dive into why you're really here. But this is an important one I really like to share. We have tons of books, we have white papers, we have blogs, we have webinars. Everything that we're researching, everything that we're doing, we publish. Excuse my pun, but we really like to be an open book. If we have the latest information on safety, we figure it's doing the world no use us holding on to it. We try and get that information out there. So if you want more information in functional safety, check out our books, our trainings. You know about these webinars, the free webinars, but we have blogs and white papers and all sorts of information to help you continue your functional safety education. But let's get back to why you're here today. All about that SIL rating, that SIL level that you may have heard about. As I said earlier, we're going to kind of start with looking at how a device can achieve a SIL and what the standards say about that. And then we're going to flip it and look at how end users use that SIL information. When we get into the topic, I usually get going, and unfortunately, I'm not the best at stopping and looking for questions. So if you do have any questions, feel free to write them in the panel, and I'll save time at the end to go back and take any questions that you may have. But let's get started and start off very basic. A lot of you may already know this, but if you don't, that's not a big deal. Let's start out with what is a SIL. You may have heard of it, but what exactly is a SIL, and how do we find what that SIL is? So a SIL is defined as a safety integrity level. It is a rating or a grade of how much risk can be removed from a system, or how well a system reducing risk does its job. Each SIL, SIL 1 through 4, is an order of magnitude higher. So SIL 1 is going to be your lowest. It doesn't have as many requirements, where SIL 4 is going to be your most restrictive, a ton of requirements going on in that. In each SIL, there becomes more and more requirements involved. When we talk about process safety and functional safety in the process industries, we normally talk SIL 1 through SIL 3. There's always exceptions to the rules, maybe rail, maybe nuclear. However, most of the industrial world is going to work in that SIL 1 through SIL 3 rating. A SIL is registered or related to a group of equipment, and that group of equipment is intended to reduce a risk for a specific hazard. And that group of equipment is usually referred to as a safety instrumented function, or a SIF. And it is comprised of one or more sensors, logic solvers, and final elements put together so that it can either automatically take a process to a safe state when some condition is violated, or it allows it to move forward in a safe process. So when we are talking about a SIL, we are talking about a rating for this group of equipment that has its job to do to protect that safety system. The main functional safety standard, IEC 61508, defines that there are 3 things that need to be determined to see if a product meets a SIL rating or not. These 3 things are the systematic capability, the architectural constraints for an element, and the PFD calculation for the product. The standard says very clearly in it, this is not a pick and choose type of activity. You can't just look at this and say, oh, I've got my probability of failure, or that PFD calculation. I have one of these circles, I'm good to go. That's not what the standard says. You can't consider only one of these circles. You can't consider only 2 of these circles or these requirements. To meet a SIL rating for a product, you actually have to achieve all of these requirements. You can think of these requirements almost as hurdles, and if you're running a race, you have to overcome each of these hurdles or barriers to finish the race. This isn't something that you just choose 1 or 2. You need to overcome or achieve all 3 of these to make a SIL rating for a product. Next, in these sections coming up, we're actually going to pull apart what each of these means. We're first going to start looking at the SIL capability, and then we'll look at what the probability of failure, or the PFD average of the product is, and then we'll look into the architectural constraints. But let's start looking at the systematic capability. This is kind of the somewhat forgotten hurdle or barrier in that the standard recommends. So systematic capability is all about quality. This is where the requirements for the quality management system come into play. The systematic capability is established by having the product's quality management system audited per all of the requirements in IEC 61508. Remember, if you are trying to achieve a SIL 1 rating, you're going to have a bunch of requirements. If you want a SIL 2 rating, you're going to have all of those requirements from SIL 1, plus a bunch of other or harder or more stringent requirements on top of that to show that you are that order of magnitude above. The systematic capability is when a third party, someone like Exida, would come in and audit the quality management system against all of those requirements, making sure that each one of the requirements is met. If any requirement in the standard is not met, the systematic capability is not achieved. This is what is really shown on the certificate of a product. The SIL, it's what's big and bold on that front of the certificate. It's on the back. You'll see SIL 2 capable or SIL 3 capable. That's talking all about quality management and systematic capability. So if we're talking about how to achieve a SIL rating in systematic capability, we would say that it is SIL 3 capable or SC3. For example. And we'll take a look later on at what a certificate looks like and how you can point this directly out on a certificate. The next requirement or barrier that the standard talks about is the PFDavg calculation, or the probability of failure. That's the yellow circle here. So the probability of failure, or the PFDavg, is a calculation based on a bunch of different inputs for that safety system, or that SIF. It includes the dangerous failure rates from each device, system diagnostics, proof test coverage, proof test how long your proof tests are going, or how often you're doing your proof tests, your test intervals. A lot of information goes into this calculation, but one piece of information that OEMs or device manufacturers can control in this portion is that dangerous failure rate. That dangerous failure rate is one of the leading variables in the PFDavg calculation, and it comes straight from manufacturers or OEMs. This comes straight from that FMEDA, or a process determined to calculate those failure rates. So if a device does go through the certification process and it has that SIL 2 or SIL 3 capability, it will have also the dangerous failure rates that go into the PFDavg calculation. Typically, we'll see maybe for a subsystem or a final element assembly, your valves, your actuators, your solenoids thrown together, that subsystem may only have a PFDavg of 1, because there's not a lot of smarts in there. There's not a lot of diagnostics. However, there are many things that can be done with diagnostics, with proof tests, coverage, with proof test intervals that can improve your PFDavg to SIL 2. We'll talk about that later on how you can improve your SIL capability rating. So with the PFDavg, there are tables directly in both IEC 61508 and IEC 61511, the two main functional safety standards. And the tables look exactly the same. It looks like it does here. And for each safety integrity level, you can see there's an associated PFDavg range. And each SIL level, or each range of the PFDavg, is an order of magnitude harder. So once again, SIL 1 will have the lowest, and it keeps on going up and up. The final barrier or hurdle, or in our visualization, our little bubbles, is the architectural constraints, the blue bubble here. And architectural constraints really is what I call our check, our unrealistic check to make sure that everything kind of falls together and is what you expect. Architectural constraints introduce some sort of minimum hardware redundancy requirements. And this is going to be considered for each subsystem of your safety system, such as your final elements would be a subsystem. Architectural constraints are looked at two separate ways. You can either evaluate your architectural constraints per Route 1H or per Route 2H. Route 1H is the original way of evaluating architectural constraints. And it talks about something called a safe failure fraction. It's looking at your safe failures over your total failures. And look at the ratio of what would be considered safe compared to what is not considered safe, or those dangerous undetected failures thrown in there. The 2010 edition of the standard introduced a second way of evaluating architectural constraints, and it's looking at the reliability data for the entire element instead of doing the safe failure fraction calculations. There are different tables for the different routes that you go through achieving your architectural constraints. For example, this is one of the tables from the standard. This is Route 1H, and this is going to let you know from that safe failure fractions calculations what your minimum redundancy may be. So to read this table, you would say, and hardware fault tolerance is that extra set of redundancy or an extra set of equipment. So if you have a hardware fault tolerance of 0, that means that you don't have any extra pieces of equipment to do that job. You have one valve or one solenoid, one logic solver, one valve actuator to shut down the process. However, if you have a hardware fault tolerance of 1, that is going to let you know you need an extra set of equipment to do the same job. Maybe you are a 1 out of 2 voting system or a 2 out of 3. That would give you one extra piece of equipment to do that same job. Whereas a hardware fault tolerance of 2 means that you need 2 extra pieces of equipment to do the same job. Right here we're talking about. So that would be a 1 out of 3 system or a 2 out of 4. You have 2 extra sets of equipment to do the same job. So to read this table, you would do the calculation from the previous slide and say how many of your failures are going to be safe compared to dangerous, or those undetected failures. So depending on your level of diagnostics is going to help the level of those safe failures that would be found or not. Let's say, for example, you did your calculation and your safe failure fraction came out to a 75. So this would put you on this row of the table if your safe failure fraction is 75. So reading this table, you can look at it and say, if I only want one set of equipment in my safety function, I'm not going to have any extra sets of equipment. Each of those pieces of equipment need to be a SIL 2. If you are going to, so then if you do need a SIL 3 in your system, if you've done your PHAs, your calculations, your LOPAs, and you decide that you need to take so much risk out that it needs to be a SIL 3, you would need, from this chart, one extra set of equipment to do that same job. And we would not be doing this in the process industry, but if you were maybe in rail or nuclear and your requirements said for that safety system, the requirements need to be a SIL 4, you would then look at this table and say, with the equipment I have, I would need at least 2 extra sets of equipment to do that same job. On the other hand, there's a second table, and this is a table for Route 2H, and it's also the exact same table from the end user's point of view. And as you can see, it takes away all of the safe failure fraction. We are no longer doing that calculation, but now we're looking at the product's historical data and the reliability of the product. Because there's no more safe failure fraction, it kind of makes it easier. You can just look at what type of demand mode you're in. If you're in low demand or high continuous demand mode, it's simply going to let you know your minimum hardware fault tolerance or that extra set of equipment that you need. So for 2H, if you meet all of the requirements and the device is 2H, it's saying for SIL 2, there doesn't need to be any extra equipment in low demand mode, but in high demand mode, you need one extra set of equipment. And it doesn't matter what demand mode you are in. For SIL 3, everybody needs at least one spare set of equipment. So now, what happens in the process, the certification process? Now that we know what the standard says and the 3 barriers you need to achieve, now what happens when you actually are doing certification? The certification process follows those barriers that we talked about that the standard requires you to meet. We start the certification with a kickoff meeting and make sure that everybody's on the same page. Then we will perform an FMEDA on the product. That's a failure mode effect and diagnostic analysis on the product, and that is where we look at the product and find every way we can possibly break it in that type of condition it will be used in. That FMEDA is what gives you those dangerous failure rates for a product. So doing that FMEDA, that will kind of help you with your PFDavg portion of the circle. That'll give you those dangerous failure rates from that. That will also help you with your architectural constraints. It will let you know what type of equipment you're looking at. Next, we do a proven in use analysis if it is a historical product. If it is not a historical product, we will look through verification and validation test plans and test results. So both of these will cover both the systematic capability, looking at if there's a lot of returns or possibly reoccurring design errors that could be changed, and also the architectural constraints of the product. Next, we're going to do the process analysis, and this is where that quality and management comes into place. We talk about we have a major program called our safety case, which breaks down every requirement that the standard requires for each product, no matter which SIL they're trying to achieve. So we just filter which SIL they want, and this will let us know all of the requirements that are there for that SIL. So that's going to definitely be our systematic or our SIL capability, and that's going to cover this circle in the certification process. Once we do that, we'll do an on-site audit. And our on-site audit really looks at all 3 of those circles. We'll look at how the quality is being done on site. We'll make sure that the FMEDA is how the device is being used, in the way it's being used, and we'll also cover the ways that the device can be configured then. Once that is all finished, we'll do a certification audit. All that is a second completely independent evaluator comes in and takes a look over things to make sure that all of the boxes have been checked, all of the requirements have been met, and they give that independent thumbs up or thumbs down. But once again, they will look at each one of these barriers to make sure that product or that device meets or has overcome each of these hurdles or barriers. The end result of the certification process is a certificate and a report. And if the device met the SIL capability, all the SIL capability requirements, if it met all of the probability of failure requirements and all the architectural constraints requirements, ta-da, you get a certificate. And as I said before, this certificate talks about all three of these requirements. But the big portion here, big and bold, is that systematic capability. Right up here, this whole circle, that SIL 3 capable on this cert, for example. It also talks about architectural constraints and probability of failure on demand on the cert as well. So now we've talked about how a SIL can be determined, how a product can go through the certification process and get a SIL for a device. And at the end of the process, you get a certificate with all great information for the end user to use in their calculations. So let's stop and take a 180. And now that we know what a SIL means, what the device, how you make it, all the people making it, let's look at how the end users use the information given to by the OEMs. How do end users actually use SIL? Why is it important to them? So SIL can be used by end users in really 4 different ways. You can establish risk reduction requirements for a system. You can look at your limits for your random hardware failures, or that PFDavg we'll talk about again. It can be used in determining architectural constraints and to establish systematic capability. So just as we did for the OEM side, let's break apart each one of these and look at how each one of these can be used or figured out. So the first is risk reduction. And risk reduction, remember SIL is that grading scale. It's how much risk is being removed from a safety system, really. So we can calculate and determine how much risk needs to be reduced by using that safety system, or we can even work backwards and find out how much risk needs to be removed from the system before you even open your doors. So the best way I like to talk about risk reduction is an example. It is just a simple calculation on how much risk you have compared to how much risk is acceptable. So say, for example, an end user did a PHA and they found out that there's this one hazard that can occur every 10 years, and that will cause a major release of toxic fumes into the atmosphere. Obviously, that's not a good idea or not a good thing to be happening, especially not every 10 years. So the company decided that 10 years is way too often. We would prefer it to happen once every 500 years instead. So all you have to do is determine the risk reduction factor from taking it from occurring once every 10 years and what is happening or could happen to the more acceptable once in every 500 years. It's easy. 500 divided by 10, your risk reduction is 50. The great thing about the standard, it provides you the charts already there for you. So you flip to IEC 61 or 61508 or IEC 61511 and you look up the SIL level and the risk reduction charts. So for our example, we fell smack in the middle of SIL 1. So for this example, you could say, well, to open the doors, you need a SIL 1 with at least a risk reduction factor of 50, because there's part of that SIL 1 that wouldn't make it. Or you could just say, I could use any possible SIL 2. The next way to use a SIL is to talk about random hardware failures and to set limits for that. Those random hardware failures come back to the probability of failure on demand, or the PFDavg. So the OEM, remember, they give that dangerous failure rate from the FMEDA. But there's a lot of pieces of information from the PFDavg calculation that end users control, such as what your proof test coverage when you're actually doing your proof tests, your mission time of a product. You also know things like your maintenance capability. Are you actually testing on time, or does it kind of get pushed out? So end users can calculate realistic probability of failures on demand. Once again, going back to the standards, they give you tables and to show exactly where you line up. If you have a certain probability of failure on demand, what SIL level you are. Once again, just like in everything else, each SIL is a different order of magnitude. So if you do your calculation, you could find you fall in the middle of SIL 1 or the middle of SIL 2. Same thing as before with risk reduction. You can specify a SIL 1 with at least this much PFDavg, or bump it up. I could be any SIL 2, but the standards are going to let you know directly where you fall into play with your calculations. The next way end users can use that SIL or that great pieces of information that OEMs give are their architectural constraints. Remember, we looked at this a little bit on the OEM side. It's the same thing for the end user side. This is going to let you know if you're using safe failure fraction, how many extra pieces of equipment you need for your to achieve that SIL that you calculated, or the risk reduction you calculated you needed. Once again, that 2H table, much simpler. It no longer has the safe failure fraction. It is just letting you know if you need SIL 3, you will be using some sort of redundancy. And then it's also used to establish the systematic capability for the SIF. So as we talked about before, the systematic capability is for each individual device that goes into your SIF. So you're going to have a systematic capability for your sensors, your logic solvers, your valves, your actuators, your solenoids, and everything in between. Your systematic capability is going to be the lowest or the weakest link in your SIF. So say you have a collection of equipment and everything in there is SIL 3 capable except your one ball valve. Unfortunately, that ball valve is not SIL rated. Then your entire safety function is not SIL rated. So this is a big one, the systematic capability. It is going to be a limiting factor, and it can limit the entire SIF if only one systematic capability is not achieved. So thinking back to that complete compliance, going into the standards, you can see the tables put together and how each SIL can be equated to PFDs or for low demand of operation. If you're in high demand, you would be talking about probabilities of failures per hour. And also risk reduction, each being a level of order of magnitude different, more requirements going into each of those levels. And once again, for that complete compliance, you can look at all of the pieces of information on the certificate. So the certificates, I know you can't see this real well, so I'm going to kind of zoom in for you. In this box right here, this is the box of information that's going to talk about those three different circles or those three barriers of information. So this is that box kind of zoomed in closer. So think about SIL capability. or that systematic capability. It's written right here on the certificate. It's going to let you know the quality management of a product. Then you're going to have your PFD. On this device, this was a simple mechanical device. This was just a simple solenoid or a valve. So we didn't say the PFD average or the architectural constraints specifically for this because there was more information needed. We needed to know what other pieces of equipment this was going to be connected to or put up with. So we said that you have to, here's the information to look up Route 1H, here's the information to look up Route 2H. If you need extra pieces of equipment, the redundancy at each SIL level. However, when it comes to PFDavg and architectural constraints, once you know all of the pieces of equipment in the system, you need to verify both of those for the entire SIF, not just this device. So now you might be wondering how you can possibly improve a SIL rating. Going back to what the standard says, you're probably sick of seeing these 3 circles and hearing me talk about the barriers, but that's exactly what you need to do. Go back to what the standard said you were limited at. How can you improve your SIL? Maybe you have no SIL at all, or maybe you have a SIL 1 and you want to be higher. What you do need to do is find out which of these barriers were your limiting factor. Was it your systematic capability or that SIL capability? Was it your architectural constraints or your probability of failure? No matter which is the limiting factor, it's okay. There are ways to improve each of these. If your SIL capability is the limiting factor, either you can buy certified, already SIL certified devices that meet your requirements, or go back to the manufacturer. They may already be in the process of doing this. A lot of manufacturers are. Or maybe you can kind of give them a hint or a nudge that say, we really like your products, we want to use them, but we need this to be in our safety systems. And that could just be going through and making sure the requirements of the standard are met. The next, if you have a maybe low or not good enough PFDavg, maybe that's your limiting factor. If that is, remember that huge equation that had so many variables in it for PFDavg. There's lots of different variables that you as an end user can control. Looking at proof testing, change your proof test interval, change how complete your proof testing is, maybe change your mission time. All of those can boost your PFDavg to possibly hit that next goal that you can obtain. So no matter where you are lacking in your SIL requirements, just remember that each of those can be looked at, each of those can be improved. It's definitely not a game changer. But all 3 need to be met and be complete for complete compliance. Remember, this is not a cherry-picking activity. You can't just look at 1 or 2 of these. You need to do all 3. Okay, so I was very bad throughout the webinar and did not take time to make questions or read the questions throughout, so I will right now. So if you do have any questions, please feel free to let me know. If you want more information on this, other blogs, webinars, we have a lot of good and a lot of free information too, even our white papers. Go on our website, check it out. We're always publishing more information. And if you really liked this and you want to learn so much more about functional safety, because we know we all do, we have a ton of classes coming up. We have them in cybersecurity, BMS, functional safety, alarm management, automotive, and we started doing online and self-paced training as well. If you can't make the whole week or come out to us, we might be able to help you online instead. So the first question we had was asking if these slides are available, and anyone that is here does get a copy of the slides sent out. It will probably be later this week. And also there is a recording of this webinar. It will be on our website and our YouTube channel if you want to go flip back and look at the recording. So expect an email from us later this week or early next week with the slides. Okay, the next question we have is, you're seeing more and more requests for SIL 1 with a single final element assembly. Yeah, we see that too. Is that a legitimate request? You're right. Sorry, let me finish the question. Is that a legitimate request, or does it look like they're going back to the first edition of a standard where a single element could be classified as SIL 3? For example, consider one actuator, one solenoid, one ball valve. So that is something that we hear often, especially when people don't necessarily know a lot that's going on behind the scenes of the calculations. When we see that, it's kind of like nails on a chalkboard for me. That's not something that we would feel comfortable advising with. You're right, it is a way. They're looking at old editions of the standard, going back, saying that this can be done. And that's the whole reason 2H was kind of brought forth in 2010. A lot of people were doing cheats around the safe failure fraction, so they were 100% safe and it was never a problem. So they made the equation harder by taking out no effect failures, but they added route 2H as well. But this also comes into play where the architectural constraints circle or barrier comes into play. Because so many people were trying to cheat the system and doing that 1 out of 1 for SIL 3, or we've even seen someone 1 out of 1 for SIL 4. And that's where that architectural constraint table comes in and says, no, this is a reality check. Just because you're doing the PFD average says you can, it doesn't mean you actually can. So ignoring that will violate that third barrier, or that architectural constraints barrier that you need to overcome. The next question we have is about the online courses. Are they up for an unlimited time, or do they have an expiration date? I believe they have an expiration date. To be honest, I'm not the expert on that, but I believe you do have a certain amount of time to complete the course. I'm sure if there was a circumstance or something that came up, we could be able to help you with that, but I believe it's for a certain amount of time that you have to log in and take the course. This is kind of a follow-up on that 1 out of 1 everything for a SIL 3, talking about could a final element be classified SIL 3 without a partial stroke diagnostic test? And I'm assuming you're still talking about a 1 out of 1 final element. And it really depends on a lot of variables that go into that equation. That's not something that I would just feel comfortable saying yes or no without getting more information. However, if we're still talking about that 1 out of 1 everything for SIL 3, that architectural constraints is going to kind of veto that. correct. However, there are ways to achieve SIL 3. If you do not want partial stroke testing, you can do your proof test more often, all sorts of way of achieving that. You can get into that in detail if you want to email me. And the next question we have, when we ask a manufacturer to provide the full assembly SIL cert, they claim they have a charge for that, so we end up getting their individual certs rather than the whole assembly. Is this acceptable common practice? I don't know what manufacturer you're dealing with, so I don't know their practices or what all's going on with that. However, if you are getting the certificates for each individual piece and you're putting them together and you're doing the calculations yourself, that is absolutely acceptable per the standard. As long as you're doing the verifications, you're making sure that everything is included, that's absolutely fine. Just when you are doing that, make sure you're looking at it closely. A lot of times those certificates will have recommended proof tests coverage and proof test durations. Make sure all of those line up so you are getting the exact values they're claiming. I've seen some certificates where it says you're getting each individual piece, you're putting them together, and it forgets pieces or leaves portions out, or the test interval is so unrealistic, it's invalid. So when you are doing the calculations, look for all of that, but it is absolutely something that you can do yourself. It's a little easier if you just buy it together, but that's definitely, if you're doing the calculations, you're looking at the tables, absolutely. We have a question about high demand and proof testing, and that's a little bit out of this webinar's scope. The proof test interval has to do a lot with the diagnostic coverage and the PFDavg, but we're also talking about the demand rate and how often the demand is going to be expected to occur, and to consider if it's low demand or high demand. If you want to go ahead and email me later, we can talk about this, or we have webinars talking about the difference between the low demand and high demand and blogs about that as well. The next question we have is that they've seen a case where a SIL 4 system was used to eliminate the use of a last line of defense due to limitations of the disposal system. Was this a wise decision? Without knowing more information, the first thing I see on that is SIL 4. If you're in process industry, except for very, very, very rare instances, SIL 4 is like nails on a chalkboard. I call SIL 4 a unicorn. Everybody said they've seen it, but has anyone really seen it? And as I said, there could be SIL 4s in nuclear or rail instances. However, when we're talking about the process industry, if someone comes to us and says, we want a SIL 4 SIF design, we go back and say, we need to look at the hazard analysis, we need to look at the LOPAs, the PHAs, how is this found? Because SIL 4 is not necessarily the right answer. We go back and have them look at a redesign. So unless there was a very specific need, I always, when I see SIL 4, I automatically, my brakes go on and I'm kind of, my attention is grabbed. It's not necessarily a decision that me or at exida would pursue. But, of course, there's always exceptions to the rules. Okay, the next question is talking about if they're using generic sensors. How would this be certified to use? So I am assuming that you're talking about generic failure rates for the system or a non-certified device. So if you are talking about a non-certified device, you can use generic failure rates to calculate your probability of failure on demand and all of that information. You can use those generic failure rates to do those calculations to see where you stand. However, if those individual products that are used in that SIF, no matter if it's sensors, logic solvers, final elements, if they don't have that systematic capability, if they don't have a certificate, or if their quality management was not analyzed, you're not meeting one of those barriers. So you're picking and choosing which portions of the standard you qualify from. So using generics are great for calculations. Using generic numbers are great for getting a good idea of where you are. However, you cannot say your safety system is fully compliant with a SIL 2 or a SIL 3 because you will not have that systematic capability. Those generic sensors that are being used, you don't know where they're coming from, who they're coming from. They could be, they could have a quality audit or issue. They could have a manufacturing issue that might not be considered. Okay, so sorry, more questions are coming in, and I think they're from previous questions, so I'm trying to go back and match them up. We talked about SIL ratings and SIL capabilities for final elements. There was a question wondering if there are logic solvers with SIL capability ratings and architectural constraints out there. Absolutely. Every device, whether it's a sensor, logic solver, final element, they will all have their SIL capabilities. So if a logic solver out there has that quality system that met the SIL capable, then their certificate will say SIL capable, SIL 3 capable on it. So the easiest way I say to look up devices if they're SIL capable or not. On the exida website, there's a link called the SAEL, and you can go to that, and that has all of the certificates, and you can look up logic solvers, and you can say, I need a SIL 3 logic solver, and it will pull down all of the SIL 3 logic solvers for you. You can look at their certificates, look at the companies, look at the failure rates, and see which one could work best for you. Okay, the questions came in a little, they were coming in at different times, and I think I got them all. If not, please feel free to email us and let us know. Thank you so much for joining us today, and look forward. I hope you look forward to some more great exida webinars. Thank you.